All right, moving on. Let's look at our next two examples. We're going to continue solving systems of linear equations with two variables, but this time we're going to look at what we call the elimination method. So our goal in solving a system is to get our equation down to one variable. So we did it earlier with substitution by picking an equation and picking a variable and solving for it, and then using that expression that we find for x or y to plug into the other equation. And then we could solve for x or y. So with that, like I said, we can get to our solution set, which is our ordered pair or intersection points of the graphs of the lines, right? If we have a consistent system. Or they could be parallel lines and we have no solution. It could be inconsistent. So with that, the elimination method says the goal, again, to get down to one variable, we're going to do that by obtaining coefficients for x or y that differ only in sign, and if we means make them opposites. Once we can get them different only in sign, once they're opposites of each other, when we add them up, we can eliminate that variable from the system, and then we can solve for the remaining variable. So we're going to try to eliminate by addition. And once we eliminate by addition, right, we get our one variable, solve for it, back substitute to get the other half, and of course check our answer. So again, you got the steps broken down for you. Now let's look at this first system. So we've got two linear equations. Now they're both in standard form. So I like that because then they lined up nicely. We've got our like terms. So right now we were to add these together. We would get 7x minus y equal 23. That's not going to help me solve it, right? I've still got two variables. So we want to add and eliminate. So let's do that. Let's go ahead and focus in on one of the variables. So I'm going to pick the x terms. Doesn't matter. You can pick x or y. One might look easier than the other based off the coefficients. Well, let's make those opposites. So what I want to do is find the least common multiple of 5 and 2. And we know that is 10, right? 5 times 2 is 10, and 2 times 5 is 10. So let's go ahead and make this a 10x and a negative 10x. So to do that, I'm going to multiply equation 1. Let's make it a 10x. So we need to multiply 5 by 2. So I'm going to take 2 times equation 1. Now I got to make sure I distribute that 2 throughout the equations on both sides, every term. So 2 times 5x, there's the 10x that we're looking for. 2 times 3y is 6y. And 2 times 9 is 18. So again, multiplying both sides of the equation by 2. And then with our second equation, we want it to be the opposite of 10. So right now we got a 2x. So with equation 2, if you want, we can put a different color. Let's multiply by negative 5, right? What's negative 5 times equation 2? So we're going to multiply both sides by negative 5. So negative 5 times 2x, that's a negative 10x, and that's what we wanted. We've got the opposites with the x terms. We add, they eliminate. Negative 5 times negative 4y, that's a positive 20y. Negative 5 times 14, that's a negative 70. And now we can add them up. So we're going to eliminate by addition. So we add these two equations together, the x terms are gone. 6y plus 20y, they add up 26y. 18 plus negative 70 is negative 52. And then what? We've got a resulting equation with one variable in it. So if we're going to solve that for y, right, all we got to do is divide out a 26 on both sides. And we've got half of our answer. So now we've got y equal to negative 2. So now we just got to find x. So to find x, we're going to go back up and substitute. We're going to do our back substitution step. Now, plug it into either of the equations. So I'm going to go back up, and I'm going to plug in here to equation 2. So let's do the back substitution step. So what does x equal? So with that equation, right, we can bring it down here. We got 2x minus 4y equal to 14. So if y equals negative 2, that implies 2x minus 4 times negative 2 equal 14, which simplifies. I've got 2x plus 8 equal to 14. That's subtract 8. We got 2x equal to 6. And let's divide out my 2. X equal 3. So when y equal negative 2, x equal 3. So my solution, right, I've just solved a system. My solution is the ordered pair 3, negative 2. Now you could check it, right? You could do a quick check step. So you want to check your answer, you plug it back in, right? Or you can graph it. For example, if you go back to the original equation, right? If you go check your answer, I'm going to do a check step. Let's plug in what we just found. So 5 times x, that's 5 times 3, plus 3 times y, 3 times negative 2, equal to 9. Well, that's 15 plus negative 6. 15 plus negative 6, 9. It checks. The same thing happens in the second equation. So again, you can do your check step, right? You can always check your work, right? Plug in the answer. But again, that's using the elimination method. So again, you eliminate quickly right from the get-go by making the coefficients of x and y differ only in sign. So let's see what happens with our next one. So we got another system, one more to look at here. And example B. And this time, let's focus in. Let's see if you want to eliminate. Well, just to be different, we can eliminate y. It doesn't matter. Pick a variable. Everything lined up nicely, ready to add up. Right now, nothing would eliminate. Well, I'm going to go ahead and notify, again, the least common multiple of 6 and 9 is what? 18, right? 6 times 3 is 18. 9 times 2 is 18. So let's go ahead and make those opposites of each other. So let's take equation 1. If we want that to be 18, we're going to have to multiply by 3. So 3 times equation 1, 3 times 2x is 6x. 3 times 6y is 18y. 3 times 7 is 21. So again, there's 3 times, right, equation 1. And then we're going to do the same thing with the second equation. We want to make a negative 18 instead of 18. So with 9, we need to multiply that by negative 2. So negative 2 times equation 2, that's a what? And we can just put it in a different color. That's a negative 6x. And that's a negative 18y. And that's a negative 40. As we add, we get what? The variables eliminate all together, and we get a statement that reads 0 equal negative 19. So we got the variables eliminating, right? We have a false statement that resulted. So we couldn't find a value for x or y. So a false statement, of course, means no solution. It means graphically, if we were to graph these two lines, they would be parallel to each other. So these are parallel lines. There are no intersection points, right, with these two equations. All right, and you can check that graphically. If you solve both of them for y, right, you get the same slope, different y-intercepts. So you've seen a scenario, each scenario, right? You've seen one solution, you've seen infinite solutions, you've seen no solution, right? So again, that's looking at our system of equations. That's using the elimination method, making those coefficients opposites of each other, and then we can add and eliminate and solve for the other variable. All right, let's take a look at an example here. Let's do a word problem. So a word problem out of our textbook. It says a total of 1210 million mobile phones and PCs were shipped out, right, back in 2006, with 752 million fewer PCs shipped out than mobile phones. How many mobile phones and how many PCs were shipped? So in a word problem, right, your first step is to figure out what are you looking for? What are your unknowns? What are you trying to find? So we want to know how many mobile phones and how many PCs were shipped out. So let's go ahead and assign that. So we're going to I'll let X equal number of mobile phones, right, shipped. All right, and I'm going to let Y be the number of PCs that were shipped. So we've got two unknowns. So it's the problem where we can use two variables, which means we're going to have to create two equations. We got to create a system. So let's see if we can solve it using a system. Now, with that said, with these two variables, we got to come up with two equations. Well, we'll go back to the beginning of this first sentence. A total of 1210 million mobile phones and PCs were shipped. So there's one equation. So if we've shipped out X million mobile phones and Y million PCs, we know that X plus Y will equal 1210. So there's my total equation. So there's one equation. And then we can look at what? The second part of the system. There's 752 million fewer PCs shipped than that of mobile phones. So that's telling us about what? Y. I've shipped out Y million PCs. So there's 752 million fewer than that of mobile phones. So that implies Y, number of PCs, is going to be X minus 752. So there's my second equation. So here's my system, right, that I've created. Now, with that said, you want to solve X and Y. You got substitution, you got elimination, you can graph them. All right, I'm going to use the substitution method. So let's solve this one using substitution, right? As we do that, I like substitution in this problem because we've already got what? We've already got the second equation rewritten in terms of X. We've already got it solved for Y. So all we got to do is substitute into the other equation. So our first step's already done for us. This one's already set up nicely for substitution method. So that's going to imply what? X plus Y, X plus X minus 752 equal to 1210. And as we simplify down, of course, X plus X is 2X. So we got 2X minus 752 equal to 1210. And again, what's resulted? We've got an equation, right, with one unknown, right, and that's X. So as we're solving this linear equation, we've got to go ahead and isolate X, go ahead and add the 752 over to the other side of the equation. So that will give us 2X equal to, what's 1210 plus 752? What do we come up with? Right, what do we get? We get 1962, right, as we add those up. And then we divide out our 2 on both sides. And X is equal to what? What's half of 1962? I got 981. Well, there's half of my unknown. So X is 981 million mobile phones shipped out in 2006. And now we just got to find Y. So we got to find Y by going back up, right, and substituting. This is our back substitution step. So we'll plug that back in. Now we can always go back to the right first step. So we know again what Y is in terms of X. So we're back substituting. So if X is equal to 981, right, that implies Y equals 981 minus 752. So again, taking out X and plugging in what it equals. And of course, 981 minus 752 gives us 229. So there's our other half. So how many PCs were shipped? 229 million, right, PCs. So we've got our two unknowns. Of course, they total up to what? 1210. If you check it and add them, you can check in the other equation. But there again, solving a system, right, or solving a word problem using a system, make it easy. So again, we had two unknowns, so we can use two variables, create those two equations, and solve it. All right. So again, that's looking at an application or a word problem, making that easy. You can see I've worked this one out step by step here in your PowerPoint. All right, let's go ahead and finish it out. So we got one more. Let's do one more word problem. Let's read through this one. Admission to the Indianapolis Children's Museum costs $5 more for an adult than it does for a child. Admission to the museum for 2 adults and 2 children costs $40. Find the cost of each adult's admission and each child's admission. So we got 2 unknowns again. So this is another problem that we could set up nicely with a system with 2 variables. So let's go ahead and assign those variables. So I'm going to let X be the adult ticket price, right? We want to know how much it costs for an adult to go in, and I'm going to let Y be the child ticket price. All right, so we got two variables, our two unknowns here. Now we need two equations. Let's go back to the first sentence. X, or admission to the Indianapolis Children's Museum, costs $5 more for an adult. So they're telling me about X in my problem than it does for a child. So X, so if it's $5 more for an adult, whatever the child's ticket price is, Y dollars plus 5. It's $5 more for the adult. So there's one equation. So that gives us that first equation in our system. Now, how about the second sentence? We can get another equation. Admission to the museum for two adults and two children costs $40. So there's the equation. So one adult's ticket is X dollars. So if we're going to buy two of those, 2 times X, and we're going to buy two child's tickets, and they're Y dollars a piece, so 2Y, going to total 40. So here, again, you've got your system, right? Now, you could, if you wanted, just to be different than our last problem, we could use elimination, even though it's set up for substitution, right? You already got it solved for X. You can plug that in the other equation. But if you wanted to do elimination, right, let's use the elimination method, right? First thing I would do in this problem is I would go ahead and rewrite this first equation in standard form. I'll go ahead and move the Y term over, right, as we do that. All right. As we do that, we go ahead and get everything lined up nicely. So X minus Y, right, equals 5. And in our second equation, which we have 2X plus 2Y equal 40. And then we make the coefficients opposites of each other. So what I'm going to do, I'm going to multiply. Let's make these Y terms opposites. Let's multiply equation 1 by 2, right? 2 times equation 1 will give us an opposite, gives a negative 2y. So it'll give us 2 times x, 2x. 2 times negative 2y is negative 2y. 2 times 5 is 10. So again, multiplying both sides by 2. So again, that's making the coefficients opposite of each other. So now we've got two equations. Right? Bottom equation is 2x plus 2y equal to 40. We add those up, what happens? The y terms eliminate. We get 4x equal to 50. So again, we can go solve it. So as we solve that for x, we've got to divide out the 4 on both sides. And we can go ahead and do that division. And we get what? X equal to 12.5. Well, there's our adult ticket price. 12.5 or $12.50 for the adult. So we got X. Now let's go find Y. So to find Y, I'm going to back substitute. So I'm going to go back up to the beginning and plug in to either of the original equations. So again, if you want to go back up to an equation, doesn't matter which one. For example, X equals 12.5, plug it in right here. So with X equaling 12.5, we get 2 times 12.5 plus 2y equal to 40. Well, 2 times 12.5 is 25, right, plus 2y equal to 40. As we solve for y, we subtract the 25 on both sides. 2y is equal to 15, right? And then we divide out our 2. So y is equal to 15 halves. And that's equal to what? 7.5. So the other adult or the other price, child's tickets, is $7.50. $5 more, but I wanted to show it algebraically, right? We knew it was going to be $7.50. Adult ticket was $5 more than the child's ticket. So again, but that's using the elimination method, just a review of that. So again, using systems to solve these word problems.